Hello and welcome to Maths with Jacob. This lesson will focus on log graphs and exponential graphs. A special puzzle to warm up the brain cells is on the next slide. The answer will be given at the end. Enjoy. What is the meaning of the following? Good luck with it and see how you go. You will have an opportunity to subscribe to my channel at the end of the video. You are also invited to share this video with your friends. Thank you in anticipation. Log graphs. The picture to the left shows the graph of y equals the log of x to base 2. If you saw one of my previous videos, you will remember that this equation can be written as x equals 2 to the power of y. The value of y represents the logarithm. We saw in that video that the logarithm is just an index. So for this particular graph, if you have y equals 0, 2 to the power of 0 is 1. When y is 1, 2 to the power of 1 is 2. When y is 2, 2 squared is 4. When y is 3, 2 cubed is 8, and so on. And when you plot those points, you end up with this log graph here. It is very interesting to note that the red graph is the inverse of the green graph. The red graph is known as an exponential graph. Note that for a small increase in x, there is a larger increase in y. This is a special feature of exponential graphs. When there is a small increase in one variable, we have a larger increase in the other variable. Now here is an example of an exponential graph which is used in real life. It shows world population. Basically, as each year goes along, the population increases. So with the increase of 1 or 2 or more years, the resultant increase in the population is quite large. And that's why it looks like an exponential graph. So human population growth approximates an exponential graph. Note the special features of the above graphs. The equations of each coloured graph is as follows. So the pink graph is y equals 2 to the x. The blue one is y equals 3 to the x. The green one is y equals 5 to the x, and the red one is y equals 10 to the x. As the base increases, so too does the steep nature of the graph. So you can see here, as the base increases from 2 to 3 to 5 to 10, the graph becomes very steep indeed. The unrestricted growth of bacteria is an example of exponential growth in real life. So very quickly, here's an example of some logarithmic functions, and that's how they look. These are the three equations here, and here are the examples of the exponential functions, which are the inverse of the logarithmic functions. And they are reflected along the line y equals x. That's like the line of reflection. So to finish off, the graph on the left shows 3 logarithmic graphs, which are here, and the 3 reflected exponential graphs, which are here. The graph above shows the general shape of each type of graph. So the important thing to note here is logarithmic graphs take this shape, and exponential graphs take this shape. Notice that this exponential graph never meets the x-axis. It becomes very close to it, but doesn't meet it, and that's why the x-axis is an asymptote. This logarithmic graph never meets the y-axis. It becomes very, very close to it. That's why the y-axis is called an asymptote. Here's a quick quiz to help you. Check with the video at any time. The answer to the puzzle, what is the meaning of the following? Summary. Isn't that a tricky one? See here the plus signs? It's the same as summing, isn't it? Doing the sum. I'll leave that to you to figure it out. Here are the answers to the quick quiz, and the video is at your disposal. If you found this video useful, please subscribe on the next slide. You will receive a notification when the next video is available. Please share with your friends. Hope to see you next lesson.